I'm presenting you with a problem about using Sklearn's AdditiveChi2Sampler for kernel approximation in a text classification task. We'll be working with a feature matrix, where each row represents a document and each column represents a word. To understand how AdditiveChi2Sampler can help reduce the dimensionality of the data, we'll explore some true, false statements to test your understanding. This statement explores whether AdditiveChi2Sampler gives you the exact same chi-squared kernel after reducing the dimensionality. We'll find out if that's true or false shortly. This statement tests whether increasing the number of components, NCOMPONENTS, in AdditiveChi2Sampler improves accuracy at the expense of more computation. We'll need to examine this carefully. This statement checks if AdditiveChi2Sampler only works with sparse, mostly empty, data or if it can also handle dense data, mostly filled. We'll figure out if it has limitations based on data type. This statement focuses on the role of SAMPLEINTERVAL parameter in AdditiveChi2Sampler, which impacts randomness and stability of the results. We'll investigate how it affects the process. This is a key concept. I want you to understand that AdditiveChi2Sampler aims to reduce the size of the data while keeping the essence of the chi-squared kernel intact. That's kernel approximation in a nutshell. I'm highlighting some important concepts to help you understand the question, such as kernel approximation, the role of NCOMPONENTS and SAMPLEINTERVAL, and what data sparsity means. These concepts are the foundation of solving the problem. This is a parameter controlling the number of random features generated by AdditiveChi2Sampler. More components mean a better approximation but at increased computational cost. Think of it like using more building blocks to build a more accurate model, but it takes longer to assemble. This parameter in AdditiveChi2Sampler controls how often we sample data during the feature generation. It affects the randomness and the quality of the approximation. A smaller SAMPLEINTERVAL might give you a more stable result, but it might also be slower. It's a trade-off between stability and speed. This refers to how much empty space is in the data. Sparse data has many zeros, while dense data is mostly filled. Understanding this helps us see if a method works better with one type of data versus another. Some algorithms are more efficient with sparse data. I see this as the number of features AdditiveChi2Sampler creates to approximate the chi-squared kernel. Think of it like this. You have a complex shape, the chi-squared kernel, and you want to represent it using simpler shapes, the new features. More features mean a better approximation but more work for the computer. It's a trade-off between accuracy and computational speed. More is better, but it's expensive. This parameter controls how often AdditiveChi2Sampler selects features. Imagine you're sampling from a giant bag of words. A small sample underscore interval means you're grabbing words frequently from the bag, and maybe you get a more representative picture of the full bag. A large sample underscore interval would mean that you pick less words frequently, and maybe you get a less stable picture. It influences the randomness of the sampling, ultimately affecting the accuracy and stability of the approximation. It's like deciding how many times you dip your hand into the bag to collect words for the approximation. This is the core problem. We're using AdditiveChi2Sampler, a tool in Sklearn, a popular Python library for machine learning, to simplify a large dataset of words and documents, maintaining the important relationships between those words as much as possible. This statement focuses on a key parameter of the AdditiveChi2Sampler. It explains how sample underscore interval directly impacts how randomly features get picked for approximation. This randomness influences the reliability of the results. Think of it as introducing a controlled level of unpredictability into the process. This is the specific algorithm used for dimensionality reduction. It's designed to work efficiently with the type of data in this problem, lots of text data, often sparse. It's not creating the data, it's summarizing it intelligently. This is the outcome of using the AdditiveChi2Sampler. The goal is to take a huge dataset of text features and turn it into something smaller, simpler, and computationally friendlier without totally losing the relationships between the words. This then makes classification faster and easier for the computer. I'm using AdditiveChi2Sampler to approximate a chi-squared kernel, a common technique in text classification where you're dealing with lots of words and documents. Think of it as a way to cleverly reduce the amount of data I work with without losing too much information. Here's the question we're tackling. How well do you understand AdditiveChi2Sampler? This question asks about the behavior of the scikit-learn's AdditiveChi2Sampler algorithm. Statement A claims that AdditiveChi2Sampler perfectly replicates the chi-squared kernel, but that's not true. It's an approximation, not an exact copy. Increasing the number of components, (n_components), improves the approximation. More detail means a better result. But that improvement comes at a price. More computing power and time. Statement C is incorrect. AdditiveChi2Sampler can handle both sparse, lots of zeros, and dense, fewer zeros, data. Although it is more efficient with sparse data. The _sample_interval parameter affects how randomly the algorithm picks features, influencing how consistent my approximation will be. A smaller _sample_interval increases stability, but it might make my code slower. This is the data I'm working with. A table where each row is a document and each column is a word. The values show how many times a word appears in a given document. This is the core algorithm I'm using to speed up calculations by reducing the dimensionality of my data while trying to retain essential information. This is the result of using AdditiveChi2Sampler, a simplified representation of the original chi-squared kernel, designed for faster processing. This parameter in AdditiveChi2Sampler controls the number of features used in the approximation. More components usually lead to a more accurate but slower computation. This parameter in AdditiveChi2Sampler controls how often the algorithm samples data. It impacts the randomness and stability of the approximation. A smaller value generally means a more stable, though possibly slower, approximation. I'm using scikit-learn's AdditiveChi2Sampler, a tool that helps me cleverly shrink large datasets while keeping important information intact. It's perfect for text classification where I have a huge number of words. The core challenge is to use AdditiveChi2Sampler to effectively reduce the size of my word frequency data for faster processing while preserving the key relationships between words. Imagine I have a giant table showing how often each word appears in a bunch of documents. AdditiveChi2Sampler helps me summarize this table, making it smaller and easier to work with without losing the essence of the word relationships. I'm going to test your understanding with a multiple-choice question about how AdditiveChi2Sampler behaves and what it can do. Let's see if you can accurately describe AdditiveChi2Sampler's properties based on the scenario. This statement checks if you understand that AdditiveChi2Sampler only approximates, not perfectly replicates, the chi-squared kernel. This explores your understanding of the trade-off between accuracy and speed. More components improve the accuracy of the approximation but require more computing power. This tests whether you know if AdditiveChi2Sampler can handle different data types efficiently. This checks if you grasp how _sample_interval affects the results and their reliability. This would have been a helpful visual aid to understand how the AdditiveChi2Sampler works. It would have shown the input, the process, and the output. This is the data that AdditiveChi2Sampler takes in, a matrix, think of a table, representing word frequencies in documents. It can handle both sparse, mostly zeros, and dense, mostly non-zeros, data. This is the core of our problem. The goal is to understand how this tool works. These are settings that control how AdditiveChi2Sampler works. (n_components) determines the size of the output, and _sample_interval controls how it randomly samples data. This is the smaller, easier to manage table that AdditiveChi2Sampler creates for us. I'm using the Sklearn libraries AdditiveChi2Sampler to handle a text classification problem. I'm working with a feature matrix where each row represents a document and each column shows how often each word appears in that document. My goal is to reduce the size of this matrix without losing important information related to the chi-squared kernel. This question is testing my understanding of how AdditiveChi2Sampler works and what I can expect when I use it. This statement is false. AdditiveChi2Sampler only provides an approximation of the chi-squared kernel. It won't be perfectly accurate. This statement is true. The parameter nComponents controls the number of features AdditiveChi2Sampler uses. More features generally mean a better approximation but also mean more computation. This is true. The parameter SAMPLEINTERVAL controls how frequently AdditiveChi2Sampler samples features. This influences randomness and affects how stable the approximation is. Different values will give slightly different results. This is false. Although AdditiveChi2Sampler is efficient with sparse data with many zeros, it can work with dense data as well. This refers to the number of random features generated by the AdditiveChi2Sampler. Think of it like the level of detail in the approximation. Higher values are more precise but more computationally expensive. This is how frequently samples are taken. Think of it like the sampling rate in audio. More frequent samples give a better representation, potentially, but it takes longer. I'm using the AdditiveChi2Sampler to approximate the chi-squared kernel, which is a way to speed up calculations in text classification by reducing the number of features. I have a bunch of documents, and I'm representing them as a feature matrix where each row is a document and each column is a word. Each cell is the count of a word in a document. This is a multiple-choice question testing understanding of AdditiveChi2Sampler in Sklearn. I need to evaluate each statement about it using my knowledge about this algorithm. Increasing the number of components, nComponents, in AdditiveChi2Sampler will give me a more accurate approximation of the chi-squared kernel. But I'll have to pay a price in terms of calculation time. It's like trying to draw a more detailed picture. More detail is better, but it will also take longer to draw. The SAMPLEINTERVAL parameter affects the randomness in how AdditiveChi2Sampler selects features. Changing this parameter will change the result and how consistent results are across multiple runs. Think of it like this. If I'm sampling from a bag of marbles, how frequently I put my hand in the bag will affect the composition of marbles I pull out, and how well the small sample represents the entire bag. This is the input matrix, where each row represents a document, and each column represents a word. The values in the matrix are word counts. This is the scikit-learn function I use to approximate the chi-squared kernel. This function reduces the dimensionality of the data while preserving essential information for the chi-squared kernel. This is the main goal of using AdditiveChi2Sampler. Reducing the size of the feature matrix to make calculations much faster without significant loss of accuracy. This is a parameter of AdditiveChi2Sampler. It specifies the number of new features AdditiveChi2Sampler should create. More components mean a more accurate representation of the original data, but with a higher computational cost. This is another parameter of AdditiveChi2Sampler. It controls how frequently the algorithm samples features. A smaller value increases the number of samples, making the result more reliable, but again potentially slower. I'm using AdditiveChi2Sampler to approximate a chi-squared kernel in a text classification problem. I have a bunch of documents, and each document is represented as a vector of word counts. I want to reduce the dimensions of this data while still keeping the important information from the chi-squared kernel. This question tests my understanding of AdditiveChi2Sampler and its behavior. This statement is false. AdditiveChi2Sampler only approximates the chi-squared kernel, it doesn't perfectly preserve it. This is true. More components mean a better approximation, but it also increases computation time. This statement is false. While efficient with sparse data, AdditiveChi2Sampler works with dense matrices too. This is also true. The sampler-interval parameter impacts the randomness of sampling, which will affect the approximation quality. A smaller interval can lead to a more stable, though potentially computationally expensive, approximation. This is my input data. Each row represents a document, and each column represents a word. The values in the matrix represent the frequency of each word in each document. This is the scikit-learn function I'm using to approximate the chi-squared kernel. It's a dimensionality reduction technique. This parameter controls the number of new features created during dimensionality reduction. More components generally lead to a more accurate approximation, but at a higher computational cost. Think of it like adding more detail to a sketch. It makes it more accurate but takes more time. This parameter affects how frequently samples are taken when creating the new features. It affects the randomness and stability of the approximation. A smaller value might lead to a more stable but more computationally expensive approximation. This is the output, a lower dimensional representation of the original data that preserves important information from the chi-squared kernel, but in a computationally friendlier format. Think of this as a compressed version of the original data, where information loss is kept to a minimum.